Very good morning, good afternoon, good evening to all the students who are taking this multi-criteria decision making course under NPTEL MOOC series. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. And as you know, this is a 12 weeks course spread over 60 lectures, each lecture being for half an hour, and in each week we have 5 lectures. So, in the last class, which was the 24th lecture, we were considering the detailed analysis in last and last to last class 23rd and 24th, we are discussing about Pareto optimality, considered that theoretically in using diagrams, and the coloring scheme was used green, orange, blue and red. And then we are going to consider, which we started, a simple problem where both were maximization. And I also did mention that if you have minimization problem or maximization or minimization maximization, when I use this word maximization minimization, I always mean there are two objective functions. It can be more than two also, there is no problem, but only trying to depict it for us to visualize may be difficult. So, continuing this lecture, if you read the slide, this is the 25th lecture under the 60 lectures series, and the broader umbrella is multi-criteria decision making, under which the main emphasis still now has been multi-objective decision making, which is more objective in nature, easy to understand, mathematical models are there and the answers which you get is easily and can be understood, communicated. Then also I mentioned the concept of, very simply, the concept of multi-attribute decision making, and we will consider further on the multi-attribute utility theory. We have already considered the simple utility functions, they would be extended. The discussions coverage would be, even though there are many points written, I think we will try to cover the concept of Pareto optimality solution in 2D space. As I keep mentioning, 3D space is fine, but 2Ds are very easy for us to communicate, that is why. We will consider the concept of effective versus inefficient solutions, the concept of Karish-Kuntakar conditions later on, scales of measurements, nominal, ordinal, interval, ratio and the goal programming. So, whatever we are able to cover in this last lecture for this 5th week, the coverage would be changed accordingly, and then all the students and participants can see the slides. So, considering the example, it was maximization and the concept we are using, the coloring schemes were accordingly. Even though when you come to the graph, we have later on, just within few seconds, which I will show, they gave you the feasible region. Based on these constraints which you have and the two objective functions, the feasible space is given in the light blue color. And I did also mention in the last class, which I will also again mention, the green and the black dotted lines are basically the objective function, and the corner points which you see, which I did mention, corner points I am just marking here in black again, and these points would be individual maximum value for the objective functions, considering the feasible region is same for both. Now, I did also mention the different coloring schemes which are used for this parallel lines. Like if you see, I will move my pointer, not mark it, because not make it cluttered. There is a brown color, optimum value 15, blue color, optimum 20, pink with optimum value 23, red optimum value 25, green with optimum value 28, and finally orange with optimum value 33. By the way, this green with optimum value 28 has nothing to do with the dotted part, or the red one optimum value 25 has nothing to do with the red dotted part. So, once I concentrate or we concentrate on this parallel movement of these lines, the situation is like this, and which we will cover one by one. When the optimum solution, when you are trying to combine F1 plus F2, if you remember, we did discuss that part, that the objective function, when there are multi-objective, you can either take a combination of F1 and F2 with lambda 1 and lambda 2, where the sum of the lambda 1 and lambda 2 is 1. Here just for simplicity, I am considering that you are just simply adding them. Even if you add lambda 1 and lambda 2, multiply to f1 and then multiply to f2 respectively lambda 1 and lambda 2, the overall concept of trying to analyze the problem would not change. Only they will basically weight the function. So, if I consider the concept of f1 plus f2, just add them. When the value is 15, I will mark it, which is this point, 15 means this one, the brown part. Then if I consider all the sets of points along this brown line, which is this one, brown I will use this dark red color, this one, consider this one. I should use, let me use this one. All the set of points along this brown line. So, I will hash it, because that is what you are going to consider. So, what are the corner points? If I consider the corner points here, 5 and 0, another corner point is 0 and 3. So, this is the one, 5 and 0, and the other extreme is 0 and 3. Now, in between there are infinite set of points joining these two lines, the brown one, the 2 points, sorry, analytic combinations, and these points like 4.5 for x1, 0.3 for x2, 4 for x1, 0.6 for x2, 3.5 for x1, 0.9 for x2, 3 for x1, 1.2 for x2, and all these sets can be verified, they lie on this brown straight line. Interestingly, if I take the objective function values f1 only first and f2 only next individually, the values of them are given respectively in row number 3 where I am putting a double tick mark and row number 4 where I am putting a triple tick mark. So, put the objective function value, find it out for x1 and x2 for 5 and 0, you will find the value as 20. So, let us double check that. So, there is no confusion between what I am saying and what is being understood by the participants and the students. So, let me write down the first function 4 x1 plus 3 x2. So, I will use the same color 4 x1 plus 3 x2 is for the first function, which I will denote as f1, and the f2 function is minus x1 plus 2 x2, minus x1 plus 2 x2. So, let us double check there is no confusion. 4 x1 plus 3 x2 for the first function f1, minus x1 plus 2 x2 is for the second function f2. So, let us check. When I put 5 and 0, so 4 into 5 is 20, 20 plus 3 into 0 is 20 again. So, here you see 20. If I put the value of 5 and 0 for f2, which means the fourth row, so that value would be minus 5 plus 2 into 0, which is minus 5, which is true. Let us consider the other extreme points, because other points can be verified. I will consider the other extreme, which is 0 and 3. So, if I put 0 and 3 for f1, which means 0 and 3 for x1 and x2, and then try to find out f1, it will be 4 into 0 plus 3 into 3, it is 9, which is 9. If I put 0 and 3 for x1 and x2 and try to find out f2 function, it will be minus 0 plus 2 into 3, which is 6, which is verified. And similarly, all the values which are there in the third row and the fourth row can be verified. Now, interestingly, if I add up these values of f1 and f2 for each corresponding values of x1 and x2, that coordinate system, which is all the points along the brown straight line. The values are 20 plus 20 minus 5, 15, 18.9 minus 3.9, 15, 17.8 minus 2.8, 15, 16.7 minus 1.7, 15, and if you continue till the last point, 9 plus 5 is 15, which means the combinations for all this set of points which are along the brown line, The coordinates may be different, decision variables may be different, but the combined objective function value is same, which means in a way you can consider that I am getting the same value of 15, gaining the same value as 15, but for different combinations of x1 and x2, which means that my level of satisfaction of getting the value of 15 is fixed, but how I can get it would basically depend on the combinations of x1 and x2 which I have, which means the set of points on the brown line are giving me the same level of satisfaction. So, I am indifferent between any points, so long the level of satisfaction is being met. Let us now come to the second line, which if you have noticed, I did not mention that if you have noticed, all lines are parallel. So, let us consider the blue one. So, I will use the blue color. So, I will use the blue color which I am hashing, and the points are as here and here. So, these points which have been marked are the corner points, are marked as 5 1 and 0 4. 5 1 0 4, let us see. If I consider the blue one point, so this would be just wait 1 minute. The diagram, but generally when you solve it, they would be the case 5 1 0. This has been not done accurately, but I will try to highlight this. So, if I consider the points of 5 1 and 0 4 for the function form of 4 x 1 plus 3 x 2. So, f 1, this is not coming up, okay, let me write it down, 4 x 1 plus 3 x 2 and f 2 function is minus x 1 x 2. So, for these values let us proceed similarly. All these points which you see, which is there in the first row where I put a 1 tick mark, second row where I put a 2 tick mark, they are always on the same blue line. They can be infinite points, I am just taking a set. And when I put these values of x 1 x 2 collectively one at a time in the function f 1 and f 2, so it will be 4 into x 1, which is 4 into 5 plus 3 into 1 will give me 23. If I put it in the function of value f 2, it will be minus 5 plus 2 into 1, which will be minus 3. Going on to the other extreme, if I put 0 and 4 for x 1 and x 2 for f 1 to find it out, and then for f 2, it will be like this respectively. It will be 0 into 4 plus 3 into 4, which is 12, correct, and then for f 2 it will be minus 0 plus 2 into 4, which is 8, which is correct. And similarly, all the values which are there on the third row, which I put a triple tick mark, and the fourth row where I put a 4 tick marks, would confirm the fact that I can get the values of f 1 as 21.9 and minus 1.9 for a value of x 1 as 4.5, x 2 as 1.3. Similarly, for a value of 4 and 1.6 for x 1 and x 2 respectively, I will get values of f 1 as 20.8 and minus 0.8. Similarly, if I go to the extreme for a value of x 1 and x 2, which is respectively 0.5 and 3.7, I will get values of 13.1 for f 1 and 6.9 for f 2. Now, if I combine them, interestingly it is the same thing comes. 23 minus 3 is 20, 21.9 minus 1.9 is 20, 20.8 minus 0.8 is 20. Go to the other extreme, if it is 13.1 plus 6.9 is 20. So, all the values, objective function values for those straight lines are same, that is the value or the net worth is same, but the combination in which I am able to get those values would differ. That means, my level of satisfaction is fixed along this blue line. Now, if I go back to this diagram which I mentioned, but just for double clarification. These lines, the brown, blue, pink, red, green, orange are all parallel to each other. That means, they would never intersect. And also another important thing is that as you move up, go on to the top right corner, if you remember the Pareto optimality 1, the orange part diagram, it was always given that we should move in this direction when it is maximization for objective function 1 and objective function 2, and that is what is happening. Is I move parallel onto the right hand side, the values keep increasing from 15, then to 20, 20 to 23, 23 to 25, 25 to 33, and so on and so forth. When I come to the optimum value of 23, I will just, without going to the diagram, if at all necessary, I will go back, but if I consider that coloring scheme which is better for me. So, the value is 20, 20 was done for the value of blue, then I come to the value of 23, 23 was given in pink. So, let us try to use pink color if it is there. It is not there, let me use another color, say for example, light green. So, the value is 23 and we will see that the extreme points which are 6 1 and 1 4. So, if I plug in these values 6 1 for f 1 and then plug in 6 1 for f 2. So, the values respectively come out to be 27 minus 4. If I go to the other extreme 1 and 4, plug 1 and 4 for f 1 and f 2, and the respective value for f 1 and f 2 come out to be 16 and 7. And similarly, all the sets of points which are there, and I will just read out few of them, as x 1 is 5.5, x 2 is 1.3, for which the respective values of f 1 and f 2 is 25.9 and minus 2.9. When the coordinate or the decision variables are 5 and 1.6, the respective value of f 1 and f 2 are 24.8 minus 1.8. Similarly, for 4.5 and 1.9 respective values of x 1 and x 2, the corresponding values of f 1 and f 2 respectively are 23.7 minus 0.7. And skipping few of these values, if I go to the third last and the second last one, values where the highlighted is for a value of x 1 and x 2 as 2.5, 3.1, the respective value for f 1 and f 2 is 19.3, 3.7, and for x 1 and x 2 as 2 and 3.4 respectively, the respective values of f 1 and f 2 are 18.2, 4.8. Now, again interestingly, if I add up these functional values f 1 and f 2 separately is 27, minus 4 is 23, which is what is written here. Then if I add up 25.9 minus 2.9, then in the next step do 24.8 minus 1.8, then next I do 23.7 minus 0.7. So, all the values add up to 23. That means, again the net value is same, but the overall decision variables can be different, but the net satisfaction level remains the same. So, considering the next optimum solution, which is f 1 and f 2 is 25. So, let us go back to the diagram which is red in color. So, I will use the red color. Oh, sorry 25, this is the 25, and the values first I will consider is 5 2 and 0 5 for the extremes, which is 5 2. I think the diagram has not been drawn very accurately, but this would be basically 5 2 and 0.05. So, if I find out and put the values individually for F1, F2 in this equation, I am not writing the equation because that has been done for the 3 sets. 5 and 2 as x1 and x2 values would give you a value of 26 for F1 and -1 for F2. Other extreme, for a value of x1 and x2 as 0 and 5, the respective values of F1 and F2 is 15 and 10. And all the corresponding values which you see in the first row, second row, third row, fourth row are respectively like this. The first row corresponds to all the x1 values, the second row corresponds to all x2 values, the third row and the fourth rows respectively correspond to individually F1 values and then F2 values. Now, if I add them, final row value which you see is F1 and F2 is 26 minus 1 is 25, which is what is adding up. 24.9 plus 0.1 is 25, 23.8, 1.2 is 25. To the other extreme if I go, 17.2 plus 7.8 is 25, 16.1 plus 8.9 is 25, 15 plus 10 is 25. So, again it is a set of points which give you the same level of satisfaction, but they can be achieved by different combinations of decision variables. Finally, without going to the details, this is basically the optimum solution when I want to find out based on the points of where the sum is 28. So, this is what line, let us make it 28 is basically the point, the green one shown, and the last one is basically orange. So, if I use the color green again, so I have F1, F2 functions values, and the 2 points, extreme points is 6, 2, 1, 5, and all the values which you see in the first row, second row correspond to x1, x2 respectively. And the third row, fourth row which I am putting a single tick mark and a double tick mark correspond to the individual values of F1 and individual value for F2 corresponding to the different combinations of x1 and x2 I take. So, when I put 6 6 for x1 and 2 for x2, the value of F1 is F30. The corresponding value for F2 is -2. On the other extreme, when I put 1 5 for x1 and 5 for x1 and x2 respectively, the values for F1 is 19, for F2 is 9, and individually all the values which you see in the third row and the fourth row correspond to the individual values of F1 and F2 when you put x1 and x2 accordingly. Again interestingly, add up F1 F2, 30 minus 2 is 28, which is exactly what is matched. Then 28.9 minus 0.9 again 28. To the other extreme, 20.1, 7.9 is 28 and 19 plus 9 is 28. Again same level of satisfaction, different sets of values for decision variables. This is the optimum solution for 33. So, it was orange in color, I will just mark it. So, the extreme point just taking is basically 6, 3, 1, 6. If you put it in F1, F2 respectively, the values are F1 for 6 and 3 for x1 and x2 is 33, and value of F2 for a value of x1 and x2 as 6 and 3 is 0. And on the other extreme, if I consider the other point, extreme means the points which I am considering along the straight line, would be for 1 and 6 x1 and x2, the corresponding values at F1 and F2 are 22 and 11, and all the respective values of x1, x2, F1, F2 are given correspondingly in row 1, single tick mark, row 2 double tick mark, row 3 triple tick mark, row 4 tick marks. And finally, when I add these values F1 for F2, 33 plus 0 is 33, matches. 31.9 plus 1.1, 33 matches. On the other extreme, 23.1, 9.9 is equal to 33, again matches. 22 plus 11 matches to 33. Now, let us consider the problem as stated below, which is a different type of maximization, again maximization, there is no change. But here I would not be going into so much details of trying to tabulate as I did. Now, the question would be, before I start, the question would be, you may be thinking that the so called set of points which gave us the same level of satisfaction. To come back to this diagram. So, these parallel lines, brown, blue, pink, red, green, orange, should they be always straight line? Answer is no, they need not be. They can be curves also, because if you remember in the diagram which I drew to basically using this 4 coloring scheme, red, green, blue, orange, they were curves, and this case was basically for the maximization one. So, when we are using the concept of maximization, obviously we will move to the right top hand corner, and these lines which you consider need not be straight line, and also the constraints, point 1, the objective functions need not be linear, they can be non-linear also, quadratic also, anything. But the idea which will be conveyed is that they would be a set of points where the value of the combination of the multiple objective function which you have would be same, but how you can achieve it would basically depend on different combinations of the decision variables which you have. So, say for example, just I am drawing a theoretical one. Consider I have x 1 and x 2, and the feasible region I am drawing in the blue one is, say for example, this, right. Now, consider the objective function can be like the non-linear. So, what we will try to achieve is consider this objective function and obviously the internal points would also be considered. It may be possible that if I want to maximize or minimize, consider that I want to maximize, it may be possible that the combination of the objective function at point A and at point B are same level of satisfaction, but the combination based on which I am trying to achieve x 1 and x 2 would be different. So, this is a non-linear part. We will consider those non-linear parts later on, but what I want you all of us to understand, and which I am trying, and maybe I am going a little bit slow, is in the sense that the objective functions here are linear, the constraints are linear. The idea which is to be conveyed in trying to tackle the problem on the Pareto optimal solutions, the concepts and trying to visualize would be same. So, even though I switched to this the nonlinear part later on, the problem which is stated here is basically again a maximization problem with the same sets of condition, and we will try to basically analyze the problem accordingly. Considering the time shortage which we have for this end of this lecture, for the last lecture and the 5th week, we would basically take this example in more details in the 6th week. Thank you very much and have a nice day.